The purpose of this video is to get a little bit more practice with quantities that we want to calculate, and calculating those quantities by first viewing them as some Riemann sum and then taking limits of these Riemann sums to get definite integrals. So today we're going to talk about finding volumes of solids of revolution. What are these objects? So the goal is we're going to take a region in the xy plane, and then we're going to rotate that region about one of the axes, either the x-axis or the y-axis. And we're going to take every point that we sweep out using that region in the rotation. And we want to then calculate the volume of this object. So to make this concrete, I have an example. Let's calculate the volume of the solid that we obtain by revolving the region bounded below by y equals 3 minus x squared, that downward opening parabola, above by y equals 5 minus x, which is a line with negative slope, to the left by x equals negative 1, and to the right by x equals 1. Okay, so I'm going to switch to a different application now, where I have drawn a picture of these things. So I'm starting out thinking in 2 dimensions, and I'm going to put the curves. So what do I have here? So I'm just on the xy plane here, that's the thing in green. I have my parabola, which is 3 minus x squared, y equals 3 minus x squared. I have my line, which is y equals 5 minus x. And then I was told in the problem that I wanted to restrict myself to x values between 0 and, between negative 1 and 1. So that restricts me to these curves. This is the parabola down here. This is the line part up here. X equals negative 1 is in blue here, and x equals 1 is in orange. And then the idea is that we want to take this region that's within here and rotate it about the x-axis. So it's going to come out at you, it's going to go backwards and sweep around. Now, I don't have the functionality to sweep this all the way around, but you can see that the picture that we should get is the following. So when we take the parabola and rotate it around 360 degrees, we get this. When we take the linear piece, the top, you're going to get this as a shell on the outside. And the sides, so this is what you get on the inside and outside, and then you get the front and back face of this object. And so you can see that the shadow of this on the xy plane, or the intersection with the xy plane, is exactly the region that we looked at, but then I rotate it around 360 degrees around the x-axis. Okay, and so our goal is to find the volume of this solid. Now, it's not just a piece of a cone, right, because it has this weird circular chunk that's been cut out of the middle of it. And so somehow we have to figure out a way to find the volume of this object. Now, we know that we've done examples before where we should be integrating cross-sectional area to calculate the total volume. But let's just go back and make sure that we know how this works in the first place. The idea, recall, was that we would take the entire solid here and we would cut it up into pieces. And the pieces I'm going to cut it up into are, well, I'm going to go ahead and slice the picture. You see these purple slices that I have here, these purple ridges. So I'm going to slice the object at those locations. Those are in purple. And each one of those things I'm going to estimate as being roughly cylindrical. Now, it's not exactly cylindrical, right? Because the side is sort of, you know, the radius at the top of this thing is different than the radius at the bottom, and on the inside, you know, we obviously have some weird dynamics, but as long as we cut small enough, these slices look like they should just be cylindrical pieces. And so then we have an estimate of this object by cutting it into cylindrical pieces with cylinders cut out of the center. So now I can take away the surface entirely, and now I'm just looking at the slices. Okay. And so now we want to ask the question, what is the volume of each of these slices? Well, suppose I take the interval from x equals 0, negative 1 to x equals 1, and I slice it into n pieces. Let's figure out what the volume of each piece is. So in order to do that, I'm going to isolate one of the slices, this one here, and let's investigate it. So it looks like some sort of disc or a washer, right? It looks like some cylindrical, some really short cylinder whose center has been cut out. Well, we can certainly calculate the volume of that. If we figure out the volume of the full cylinder, if I hadn't taken the center out, and then subtract the volume of this center cylinder, then that'll give me the volume of this entire disk. And then in order to get the volume of the entire object, or the estimate of the volume, I would just add up all of the volumes I get from each slice. Okay, so, well, in order to calculate the volume of this thing, like we said, we need to calculate the volume of the sort of outer, the big cylinder. And you know that the volume of a big cylinder is pi times its radius squared, which is the area of the base, and then you multiply by the height. Now the height is the thickness of this thing, and that is our delta x. It is our 2 divided by n, if n is the number of regions or the number of intervals we cut the total interval into. So the height is delta x. The only thing we need to know is what is the radius here. Well, the radius of the outer cylinder is you go from the origin, or at least from the x-axis, all the way up to this blue line. So it's this blue line's function evaluated at a point that's in the interval here. And similarly, to get the volume of the inner cylinder, you should take pi times radius squared times delta x, where the radius is now, it is the distance from the x-axis up to this pink curve. Now, that slice is going to be different if we shift our perspective. So let me give an example here where instead of being at b equals 0, if we were at b equals 0.2, and it takes a moment, then this gives us a new cylinder, and you can see the inside's radius is given by going from the x-axis up to the pink, and the outside's radius is given by going from the x-axis up to the blue. And so if we slice this and keep doing this procedure at different locations, we're going to get different disks, and when we add up the volumes of each of the disks, we're going to get the volume of the entire, well, we're going to get an estimate of the volume of the entire object. And as you can guess, if we were to take, and this will take just a moment with the computer, but if we were to take more, if we were to take thinner slices, meaning we take more more slices, so that means each one is thinner. So if I change this width to 0.1, and it'll take a moment because it has to render a lot of parametric curves that I've put in here. But in a moment, I promise it'll come up. There we go. Now we've taken more slices and we get a better resolution. We get a better idea of what this object looks like. And this estimate that we take with more slices is going to be a better estimate. Okay, so let's go back to the mathematics. Let's put this in presentation screen mode. So to calculate this, let's go ahead and write f of x to be 5 minus x, that's the upper curve, that's the blue one that was bounding everything at the top, and g of x to be 3 minus x squared, that was the downward opening parabola at the bottom that was purple. In total, we found that we can approximate the volume by doing this. We took pi times, well, the radius, the outer radius, was given by looking at a point that was on on the graph of this function. So that means the y value, which is the distance from the x-axis, is 5 minus an x-coordinate, which is in a given interval. So this would be the radius of one of the slices, the f of xi would be, and then you square it and multiply by pi to find the area, and then you're multiplying by the width, which was the total width of the total interval divided by the number of pieces we slice it into. And then, of course, I have to take away the stuff that's on the inside. So that's, again, a cylinder. It's pi times the radius of the inside squared times the height, which is 2 over n. But that's just one of the slices, and we have to do this for all of the slices, so I'm going to sum up from I equals 0 to n minus 1. Okay, so let's just ingest this for a moment. We have volume of the outer cylinder minus volume of the inner cylinder. Now, these 2 over n's, these are our delta x's, because we split the interval from -1 to 1, which has width 2, into n pieces. So in total, our width, our delta x, is 2 over n. And so if we factor that out to the right-hand side, we can see that we get a Riemann sum. And so we'd like to take the limit of this Riemann sum. And what does that give us? That gives us the integral from, in that case, -1 to 1 of pi times the outer function squared minus pi times the inner function squared. And that delta x becomes, as we've seen many times, dx. So that example gave us a way to figure out the general formula for solids of revolution. If I take a region and I say that region is bounded on the left by x equals a, on the right by x equals b, above by f of x, and below by y equals g of x, then to calculate the total volume, I simply calculate the integral of this quantity. But again, you can memorize this as a formula, but it doesn't really make sense to memorize it as a formula. Instead, think, how did we get here? We got here because we sliced into pieces. Each piece was a cylinder that had a cylinder removed. So we could calculate the volume of said cylinders by pi times radius squared times width. And so we took the difference, and then we added up, and we noticed that this is a Riemann sum. And so with that observation, we can turn it into a definite integral. Okay, so I'll let you go for a generalization where instead of rotating about the x-axis, you could rotate a region about the y-axis, and that you'll talk about later.